the first time, scientists have detected ripples in the fabric of space and time, known as gravitational waves, from a colliding pair of dead stars called neutron stars. This is the first time astronomers have witnessed two neutron stars merging, and these new findings may help solve the decades-old mystery of how many of the universe's heavy elements were created. Here's an explainer on why the discovery is so groundbreaking for our understanding of the universe. The existence of gravitational waves was first predicted by Albert Einstein in 1916. According to Einstein's theory of general relativity, gravity results from how mass warps the fabric of space and time. When any object with mass moves, it should generate gravitational waves that travel at the speed of light, stretching and squeezing space-time along the way. Gravitational waves are extraordinarily weak, making them extremely difficult to detect, and even Einstein was uncertain whether they really existed. A century later, in 2016, researchers successfully detected the first direct evidence of gravitational waves, using the Laser Interferometer Gravitational Wave Observatory LIGO. This work earned 3 scientists the 2017 Nobel Prize in Physics in October 2017. Credit by Cult 8, infographics artist. LIGO uses a pair of detectors in the United States, one in Livingston, Louisiana, and the other in Hanford, Washington, to sense the warping that gravitational waves cause as they move through matter. Each detector is shaped like a gigantic L, with legs about 2.5 miles 4 kilometers long. The legs of each detector are normally the same length, so laser beams take the same time to travel down each. However, if gravitational waves pass through Earth, and they make the detector legs expand and contract by as much as 1/10,000th the diameter of a proton, these space-time distortions allow each detector's instruments to detect the split-second differences in time it would take for the laser beams to zip down one leg of the detector versus the other. Because LIGO's detectors are separated by about 1,865 miles 3,000 kilometers, it can take up to 10 milliseconds for a gravitational wave to cross from one detector to the other. Scientists can use this difference in arrival times to gauge where the gravitational waves come from. As more gravitational wave detectors come online, such as the Virgo facility near Pisa, Italy, researchers can do a better job of pinpointing the sources of gravitational waves. The easiest gravitational waves for LIGO to detect are the most powerful ones, which are released when extraordinarily massive objects collide with one another. All of the gravitational waves that LIGO and other detectors previously discovered were from the mergers of black holes. Now, for the first time, scientists have detected gravitational waves from merging neutron stars, using LIGO and Virgo. Neutron stars, like black holes, are remnants of stars that perished in catastrophic explosions known as supernovas. When a star goes supernova, its material collapses to form a dense core. If this core is massive enough, it may form a black hole, which has such a powerful gravitational pull that not even light can escape. A less massive core will form a neutron star, so named because its gravitational pull is strong enough to crush protons together with electrons to form neutrons. Although neutron stars are typically small, with diameters of about 12 miles 19 kilometers or so, they are so dense that a neutron star's mass may be about the same as that of the Sun. A teaspoon of neutron star material has a mass of about 1 billion tons, making neutron stars the densest objects in the universe besides black holes. On August 17, Advanced LIGO and Advanced Virgo, the current upgraded versions of both observatories, detected a gravitational wave signal possessing an extraordinary amount of energy, something like 1 billion times the energy of the luminosity of the Milky Way, said Nancy Caslerwell, of the California Institute of Technology in Pasadena. Caslerwell is principal investigator of Global Relay of Observatories Watching Transients Happen Growth, an international collaboration focused on cosmic transient events such as neutron star mergers. Its energy was enough to outshine the 100 billion stars in our galaxy by about 1 billion-fold for the 50 or so seconds it took place, said Caslerwell, one of many scientists who took part in this discovery. This event is the first time scientists have witnessed two neutron stars merging. One main clue that the signal came from such a merger was its duration, the longest gravitational wave signal detected to date, Caslerwell said. Black holes are denser than neutron stars, so the signals from their mergers are relatively brief. Previously detected black hole mergers lasted for a second, maybe 2 seconds, Caslerwell told Space.com. This latest event lasted nearly a whole minute. There was another main clue that this new signal came from a neutron-star merger. The masses of the objects generating these gravitational waves. The frequency of gravitational waves depends on the mass of the object that generates them. The higher the frequency, the lower the mass, Castlewell said. The two merging objects that generated this new signal were about 1.3 and 1.5 times the mass of the Sun, respectively, which is typical of neutron stars, Castlewell said. In comparison, the first black hole merger that LIGO detected involves black holes each about 30 times the mass of the Sun, Castlewell said. As powerful as this new signal was, it was also much less powerful than ones seen from black hole mergers. This neutron-star merger converted about 0.025 times the mass of the Sun into energy, which is a stupendous amount of energy, Castlewell said. However, the first black hole merger LIGO detected converted 3 solar masses into energy, which outshone everything we had ever seen until then, Castlewell said. So far, LIGO has detected 4 black hole mergers and 1 neutron-star merger. Some researchers had predicted neutron-star mergers would be more common than black hole mergers, whereas others had predicted the opposite, Castlewell said. She explained that while neutron-star mergers are more common in any given volume, black hole mergers are more energetic and so can get detected from much farther out. Together, Advanced LIGO and Advanced Virgo narrowed down the location of this new event, named GW170817, to a 28-square-degree patch of sky. In comparison, the full moon as seen from Earth covers about 0.2 square degrees of sky. By working quickly, astronomers used both conventional and gravitational wave observatories to watch the same event, the first ever detection of light from a gravitational wave source. In contrast, black hole mergers are not expected to produce any light, which means conventional telescopes cannot detect them. The scientists employed a variety of telescopes to analyze the radio waves, infrared waves, visible light, ultraviolet light, X-rays and gamma-ray burst from the neutron-star merger for weeks. The SWAP-A telescope at Las Campanas Observatory in Chile successfully pinpointed GW170817 to a galaxy called NGC 4993, located in the constellation Hydra, about 130 million light-years from Earth. This is the first time scientists have linked a gravitational wave event with a known galaxy. They dubbed the source of this event SWAP-A Supernova Survey 2017 ASSS-17A. Using LIGO and Virgo, we found there were only 49 galaxies that could have possibly been the home of this merger, and by prioritizing our search for this merger by how massive the galaxies were, which helped us estimate how many stars there were in each galaxy, and thus the chances they might have merging neutron stars, we found the merger in the third galaxy on our list, Castlewell said. SSS-17A quickly faded and changed from blue to red light, a sign that its debris expanded rapidly at speeds close to the speed of light and cooled as it went. The researchers said the merging neutron stars generated a kilonova, an explosion 1,000 times stronger than a typical star explosion, called a nova. We think the merger ejected about 10,000 Earth masses of material, Castlewell said. The researchers estimated the merger generated a jet of material that shot outward at nearly the speed of light, moving down a path tilted about 30 degrees away from the line of sight from Earth. All of the light that the researchers detected came from a cocoon of material surrounding this jet. They estimated that about 30% of future neutron-star mergers will generate bright gamma rays detectable from Earth. The spectrum of light from the matter ejected from the merger revealed that this material was loaded with newly synthesized elements. These new findings confirmed 70 years of research suggesting that neutron-star mergers are powerful enough to synthesize heavy elements such as gold, platinum and lead. Scientists had known where lighter elements were synthesized. Most hydrogen and helium came from the Big Bang, and elements up to iron on the periodic table are mostly forged in the cores of stars. However, the origin of half of the elements heavier than iron has been uncertain. These new findings provided the first concrete proof that such mergers are the birthplaces of half of the universe's elements that are heavier than iron, Castlewell said. It remains uncertain what the product of this merger was. It's about 2.7 solar masses, so it lies in the mass gap between neutron stars and black holes. The most massive neutron stars found to date are about 2 solar masses, and the least massive black holes seen are 5 solar masses, Castlewell said. It's either the most massive neutron star ever seen, or the lowest mass black hole ever seen, or maybe it's a supermassive neutron star that will collapse to form a black hole. This is new territory. The scientists detailed their findings in a collection of papers in the journal Science, Nature, the Astrophysical Journal and other journals. Follow Charles Q. Choi on Twitter at Choi. Follow us at space.com, Facebook and Google. Original article on space.com.